My name is Lawrence Clark.
My name is Deepam Rana.
And my name is John Ewan.
And for our Engineering 305 project, we chose to create the ARC-170 starfighter from the Star Wars universe.
The ARC-170 is a starship used by the Galactic Republic in the Star Wars universe. It has 3 seats and 2 engines, along with 1 large cannon on each wingtip. It has 2 smaller wings on each wing that fold open when the fighter is engaged in combat. To model the ARC-170 starfighter, we split it into 3 sections. The fuselage was modeled by Deepam, the engines were modeled by Lawrence, and the wings were modeled by John.
So this fuselage is actually not the same as the original ARC-170. We actually found an online fan edit with real engineering drawings, so we based a lot of it off of this. So moving on, let's talk about what I actually did. So my fuselage was misleading in terms of difficulty. When I initially started, I thought the cockpit would be straightforward and that the hardest part would be my fuselage itself. Instead, it was actually the exact opposite. So let's go over the 2 easier parts first. So here we have the fuselage. I had to split it up into 2 parts mainly because of the ease of design. So let's start first with the top fuselage. The top fuselage was actually fairly straightforward. I initially started using GSD, but realized that that would not work fairly quickly. So instead, I switched to sketch tracer and part design. I started with 2 sketches, one at the top and one at the bottom. I then used solid combine to make the first initial design. Once that was done, I started adding what I call just GSD touch-up designs, which is mostly all the side work. After that, it was almost completely done, and all I did was add color and stickers. So moving on, let's talk about this bottom fuselage over here. This part was actually extremely straightforward, and there was really nothing too difficult about it. I made that small rectangular part just out of part design, and used GSD to make that ovular part. And using that, I just used a fill-in join tool mostly. And finally, this is the cockpit, and it was definitely my most challenging part. When I initially saw it, it looked straightforward, and I thought I could even make it mostly in part design. However, I quickly realized that this was not the case. Part design would have never worked because of the odd surfaces. The first being the windows, and the second being the connecting point between the first and second window. Instead, I had to start with 1 simple rectangular block, make several cuts, and then use GSD for everything else. I started with using GSD to make that window area. I used the spline tool and sketch tracer to sort of just sketch the outer surface of it, and then used the fill tool to make one big surface. After that, I redid that for the 2 other windows, and then had to use GSD again to connect it between the first and second window.
Despite being a starship, the ARC-170 actually has turbofan engines mounted on either side of the fuselage. The engines consist of 3 different sized turbine fans, as well as 4 engine subsections. These sections include the front casing, the middle casing, the rear casing, and the turbine shaft. A turbofan uses combustion to rotate rear turbines, which in turn drive a larger frontal fan. This system is continuous, as the faster the rear turbines drive the front fan, the more air the front fan sucks in. This causes the rear turbines to spin faster, again driving the front fans faster. The majority of the thrust is actually caused by this frontal fan. This picture shows the side view of the engine used in the ARC-170, with the hidden line displayed. As the picture in previous slide shows, the engine can be divided up into 4 sections: the front casing, the middle casing, the rear casing, and the turbine shaft assembly. The middle assembly consists of the fuel lines, the blast chamber, and the middle casing. As this image shows, the casing has multiple connection points that attach to the front and rear casings, as well as keeping the drive shaft in line. The fuel lines are placed around the blast chamber at equal intervals. Whilst the details of the fuel system were not included in the final design, we thought it was important to show where they would be in a real turbofan engine. This image shows the turbine shaft assembly. As stated earlier, the front fan set produces most of the thrust due to its larger size. The second fan set occurs right before the blast chamber. The purpose of this fan set is to draw air into the blast chamber increasing the pressure in there. The third set of fans occurs right after the blast chamber. As the blast chamber expands the gas rapidly, it drives the third set faster, which in turn, because they're all connected to a drive shaft, increases the rotational speed of all four fan sets. The final fan set occurs in the afterburner in the third section of this engine. The third section is the rear casing, and whilst the details of the afterburner are not shown, we felt it was important to include where it would be in a real engine. The main fans are curved, whilst the fans located in the middle and rear casings are straight. However, like I said, they are all connected by a single drive shaft. The fans are also connected in pairs, as the image shows. This is to increase the force that they can, or the thrust that they can exert. As this project was submitted for an advanced CATIA class, we felt that it was important to include kinematics in the engine assembly. Now, the kinematics we used included the drive shaft and the fans rotating inside of the fixed engine housing. As this short GIF shows, all four sets of fans are connected and locked into place with their drive shaft and the nose cone. As the drive shaft turns, then all four fans turn at the same speed. This is the final rendering of the engine. Whilst we could have chosen to use materials, we felt that it was important to keep the general aesthetics of the ARC 170 in line with each other. So we made the engine casings white, the rear casing gold, as well as the fuel lines and the nose cone, and we kept the fans as a chrome. This is a rear rendered view of the engine used in the ARC 170 Starfighter. Now, unlike the other views, this one shows the connection points between the multiple casings. The connection points are in sets of 3, and they occur at multiple intervals throughout the entire engine. You can see these connection points because they're the white bars that connect the two different types of casings. Now, there is a connection set in front of the middle casing. This stabilizes the front fan used in the turbofan engine. There is a connection set between the front casing and the middle casing, and there are also connection sets inside of the middle casing that lock the drive shaft into place. There are also connection points inside of the rear casing, however they are not shown in this view. These connection points are very important to the engine's overall efficiency and stability because they limit vibrations and they keep everything rotating around a central axis.
The ARC 170 has two wings, which assist in generating lift in atmospheric flight and serve as a mounting point for the main cannons. Unlike most modern aircraft, the wing cross-section is not airfoiled, so they were modeled as a flat plate with filleted edges. The planform shape of the wings are ellipsoidal, which help with efficient wing loading while in atmospheric flight. The S-foil winglets will open up to reveal radiators when the aircraft is in combat. This will help increase the cooling power for the extra heat generated by the weapons. Additionally, the connection point between the cannon and the wings is made using a circular joint, which allows the weapons to rotate inward to assist weapon convergence. The wing subassembly consists of three main parts: the central wing, the two winglets, and the cannon. The central wing was modeled by tracing its profile using the sketch tracer toolbench, and then completing the rest of the features using generative shape design. The hardest part of modeling the central wing was the mounting point between the wing root and the engine casings, which involved multiple different curved surfaces in order to maintain the curvature of the ARC 170's wing and also allow it to mount against the curved casings on the engine. The main wing also has a hole in its central area where a radiator is placed to aid with heat dissipation. Additional auxiliary radiators are also located on the inner surfaces of the wing's S-foil winglets. When the S-foils are folded out as pictured, these radiators are exposed to external conditions, which will aid the aircraft in dissipating heat generated by its cannons while in combat. These S-foils were also modeled by tracing their main profile using sketch tracer and using GSD to help with creating the curved joint by which these S-foils attach to the engine casings. The cannon was also modeled using sketch tracer, which was used to get the main length and diameter dimensions, but most of the details on the cannon had to be done just visually by looking at pictures of it and making a model to as close as possible as the pictures showed. The cannon is also connected to the winglet, or to the main center wing, using a cylindrical joint. This allows for the cannons to rotate inward to aid in weapon convergence, which is often a problem on military aircraft which have their cannons mounted far apart. This is the final rendering of our ARC-170 starfighter. The colors pictured were obtained by right-clicking individual surfaces and selecting color options rather than applying paint materials. This allowed us greater control over the colors of components on this aircraft without overcomplicating the part and assembly design. The aircraft was positioned at a positive angle of attack with a negative roll relative to its body fixed frame in order to obtain this attractive angle.
In order to accomplish the goals set forth in this project, team meetings were a frequent occurrence, as well as updates via Google Drive. Dates were set for specific project milestones, and it was the responsibility of each team member to meet these deadlines. Coordination between team members was necessary, as the three sections of this project are all interlocking. Overall, our team worked together very well to accurately create and assemble this fictional starfighter.